Momentum, Chapter 8, 8.1 through 8.3. You have already done the momentum notes, momentum equation. You reported what these were in class and did some practice problems. I think it was on 138, you did questions 1, 2, 24, 25, and 28, just to practice, make sure you understand. Today we're moving on to impulse. Alright, included in impulse, you should define it, provide an equation, think about what all these letters represent, talk about practice. Again, it comes up with a few more letters. This is kind of review down here. Talk about the different units, provide examples. So we're going to move quite quickly. So please pause the video where you need to. We've already done momentum. We're going to impulse. Impulse changes and changes momentum. We'll talk about bouncing, conservation, collision, next class. All right. As time passes, with force being applied, is going to change the momentum of an object. This happens, we often call it an impulse. So the formal definition of an impulse, yes, you have to write it down. The formal definition of an impulse is the measure of how much force is applied for how much time. And this impulse is equal to your change in momentum. So if you're increasing momentum, that's because of the effect of the impulse. All right? Force applied over periods of time create an impulse. A great example would be if I took an egg and I threw it at the wall. The impulse will be a very short time frame, but my force is going to be the same in both situations. So I throw it at a wall. The egg smashes into a million pieces. Well, my impulse is going to be less. It's going to have less momentum, be less effective if I throw that same egg at a big laundry sheet, or not a laundry sheet, but a big, like, queen-size sheet. You're holding it up between a friend, and a third friend throws it. No matter how taut you try and hold the sheet, if you're not holding the bottom, it's going to absorb some of that energy or some of that movement from the egg and prevent it from breaking. It's also why when you catch, if you've ever played the egg toss game, you cradle it, you bring it in towards yourself. Same with basketball, you bring the ball towards yourself to increase your impulse, to increase the amount of time, so that way the force doesn't make as much difference. Again, here's your tennis player. The force being applied is the effect of this tennis racket on the ball, right? So if he follows through, he's also increasing the amount of time, that amount of connection between the ball and the racket. That increase in time and force is what makes such a powerful shot, whether it's hockey or whether it's baseball, whatever you're talking about, that follow through increases your time. Okay, so here's the equation. It is impulse is equal to force times change in time. All right, it's not an instantaneous moment, it's a change in time. All right, that's what this delta, it's that triangle is delta t. That change in time implies it's not just one singular time. The impulse is measured, the unit for impulse is Newton seconds. It doesn't have anything fancy or special, just Newton seconds. So when your force is small but you increase your time, it would equal the same as if you put a great force in a short amount of time. All right? So when we're given an equation, imagine a force of 2 newtons is applied to an object for 3 seconds. It's straight plug and chug, folks. Pay attention to your units. This is force, this is force. So I would take force and plug it in here. I would take seconds and plug it here, right? And multiply. 2 newtons times 3 seconds is 6 seconds. Okay, moving on. Notice sometimes this is a little bit choppy, so bear with me here. Okay, another plug and chug. Pause the video and try this on your own. Figure out where each thing goes. You have 15.32 newtons with a time of 3.45 seconds. What's the impulse? Pause it, try it, then unpause, check it. So if you plug and chug, 15 times 3, there's your, well, I left out the decimals. It's 52.85 seconds. Okay, now we're throwing you off here. Pay attention to the units. This is where a lot of people get hung up. This time it's giving you the impulse as an impulse of 39.5 newton seconds in 16.11 seconds. So they're telling you the impulse but not force. They want you to solve for it. So you are going to have to get force all by itself. Divide both sides by delta t. All right, divide by delta t. And then plug and chug. So now force is equal to impulse divided by time. And here is your math. All right, do your division and you get 2.54 newtons. Okay, impulse changes momentum. All right, so the greater the impulse, the greater the momentum. So if I spend 10 minutes applying 10 newtons of force to anything, if I have a desk chair, and I spend 10 minutes pushing it at 10 newtons of force, it's going to get rolling. It's really going to move, all right? If I only do it for 5 minutes, it's not going to have that force to get it. It's not going to have the impulse quite as much, all right? That momentum or change in inertia or change in speed is not going to be as great with only 5 minutes of pushing, right? There's your math. They took minutes and turned it into seconds. 600 seconds is 10 minutes, 300 seconds is 5 minutes, and then they plugged those numbers in and got your impulse. Okay, now why they did that is you can take impulse right here and you can apply it or use it to help you solve for your momentum. So impulse and momentum are kind of the same. The amount of impulse you have can change the amount of momentum you have. Greater the force, the greater your momentum. But if you decrease the time, that's going to also change the effectiveness here. So please write this down. They can be equal to each other. Note, the greater the impulse, the greater the change in momentum. So you can really be booking it if you have a greater impulse or a greater force. Okay. Don't forget, delta is change in. So the change in mass or the change in velocity will affect the impulse here as well. Impulse can be exerted to increase or decrease the amount of momentum, right? So if a car is coming at you, if you start slowing down earlier, you're increasing the time in which you're going to hit something, right? Or if you change your velocity here in the same case, change your velocity, start slowing down, it's going to affect your impulse, your impact, hit something. So you hit something, that's your impact. The impulse is the force and how much time you took to take it. Right? So details, impulse, force, time, mass, here are all the components you're going to need in this chapter. It's a biggie. So impulse will also affect the impact that you have on something. All right? You increase the force, decrease the time, your impact is going to be different. So if you saw in the picture of the guy getting punched in the book, so thrilled. You increase your force and decrease the time, it's going to have a much greater impact on his face. All right, how his face is going to look after will be dramatically different. So if you slow down your punch, if you do a slow motion punch with the same amount of force, it's not going to have that same impact to his poor face. Right? Other plug and chug. Please pay attention. This is something else that will trip some of you up. Look here. This is a velocity. This is another velocity. Notice we're doing the change in velocity. So you would have the 4 minus 14 minus the 4 number. I didn't put all the numbers in because I'm using my mouse here. Right? Here is time. Notice it's seconds. That would go here. And then we have mass. That's going to go here. You want to get force by itself. So they did the algebraic step, dividing both sides by delta t. So by dividing delta t over here, we left F by itself. Delta t over here. Don't forget to do your math to solve for the change in velocity. This is change in velocity. How did the two vehicles, or how did the vehicle change? Right? So that will allow you to determine the amount of force that was applied in, say, a car accident or whatever you're trying to solve. Okay. Please note, you apply a small force for a long time, it can be as effective is a huge force and a small amount of time. All right, a huge force is usually, in this case, going to do, if there's a huge force, a big old wall or something on this. Oh, go back. There's a big old wall on this. It's going to create a lot more damage than if you're slowing down and moving a lesser force. Okay, so let's see how this applies in real life. Nowadays, all cars come with safety features like this little airbag. Think of this like sheet situation. Your head is the egg. All right, when your poor little egg head hits this flat steering, there's not a lot of give for it to go. All right, it's stuck there in place. So it's essentially, at some forces, it's like hitting a brick wall. You have a huge amount of force because of that inertia. Remember, your body needs to continue moving forward, even though you can't buy a car. So that your poor egg head is going to be smashed into bits, just like this poor steering wheel. Where here, the time in which your egg head comes into the sheet, it's protecting, it's providing you a greater amount of duration before you slam into something, or preventing slamming into it at all. Okay, so this is for protection purposes right here. This, on the other hand, would be for athletic purposes. Increase the momentum, increase the force, or shorten the time at which things are applied will change the momentum of something as well, usually fast increasing it, which is what you want in a baseball, or throwing a football, or kicking a football. Okay, here's your video. Notice this guy, if he weren't rubber, he'd be smashed in. Where his face is still smashed, it's hitting more of a cushion pocket. It's protecting a little bit more. Same thing here. If you've ever seen these big yellow components, some of these are designed to crumple, provide you a little bit of time before you slam into something hard. Okay, here's another situation like sports. Okay, so when we're playing sports, if you increase the velocity of your bat or increase the mass of your bat, that will increase the amount of momentum you have when you're hitting a baseball. You're going to bunt, you decrease the velocity of the bat, or you change mass of the bat to affect how what momentum is going to be applied on this ball. Here is a similar situation. We're showing you the home run versus the bunt. Okay, remember, force is equal and opposite. So the force here cannot truly be changed because the force applied on the ball by the bat is the same applied by the bat and the ball. Learn that force pairs in the last unit. What's the difference between these two is his follow-through allows a greater amount of contact time interval in which the ball and the bat are interacting is increasing, allowing such a dramatic change. Where here, same pitch, but he's controlling the bat, and directing the force in a different direction and decreasing the time interval. So thereby decreasing force or contact. Okay, here it talks about that. You have a pulse. This is your impulse. And it's showing the effect of force with the different amount of sustained time by just following through, like 0.002 seconds. That's what we're seeing in baseball. You're going to dramatically change the force. That needs to be a